Okay, good afternoon. Welcome to class. Yebu. Today we're going to look at regression. We started regression last week and correlation. We're going to look at regression and take it a notch higher to multiple regression. So last week we said regression is trying to find a way or an equation or a model that relates the dependent variable to the independent variable, whereby you have, now I need to get my board. Okay, share screen. Yeah. So you have a dependent variable, which is usually given as y. You have an independent variable, given as x. So you're trying to find a relationship or a model or equation whereby you can predict values of y given x. And for the simple linear regression, you will only have one independent variable and one dependent variable. So you should be able to say which one is your dependent variable, which one is your independent variable. And the equation that relates them will be y equals to beta naught plus beta 1 x plus error term. Or you can write yi beta I ai. Now, there's some conditions that have to fulfill for this to work out, which we're going to talk about. But then, when you analyze your data, you have what comes out as a regression analysis. Okay, I think we should open to, I'm trying to see now, which one? If you go to Moodle, your lecture notes, I'm just trying to see which one is which. Week 8 lecture slides on simple regression. Now, when you run your regression analysis, how do you read your values for beta naught, beta 1? If you go to your week 8 lecture notes, you have the least square estimation model and the coefficients. Under the coefficients, you have the first column gives you the model with your constant. Your constant in this case is your beta naught or your y-intercept. So from your model giving, you have this as your constant. Or y-intercept. You have the beta 1 given, or is the slope. In this example, we had years of employment at a company called Beta. Against y, which is our dependent variable, sorry. So in this case, your beta naught is given as 21.458. You always read your beta naught under unstandardized coefficients. Unstandardized coefficients. You have your beta and you have your standard error. Your beta naught is 21.458. Your beta 1 is 3.049. So in this case, your estimated regression line is given as y equals to 21.458 plus, you're having a plus because your beta 1 is 3.049. If it was a negative number, you have minus here, plus 3.049x. That's your estimated regression line. Is that regression line or model? Now, given this regression line, if we're given the values of x, you can plot the values of x here. Let's say when x is 20, that's y equals to 21.458 plus 3.049 times 20. That gives us 82.438. Any question, please? Any question? Okay. Next, we want to look at the conditions you have to use. The conditions you have to fulfill in order for this to apply. The first condition we're going to look at is that there must be a linear correlation between x and y. So there's no need of trying to get estimated regression line when variable y does not depend on x. So for instance, if your salary increase does not depend on the number of years you've worked with an establishment, then you cannot fit a regression line. So that's the first condition. There must be a linear correlation between them. Second condition is that values of y, each value of y does not depend on the other values of y. So there is independence. There's independence. So the values of one y does not depend on the value of other y. Number 3, for any value of x, y has a normal distribution. Remember our normal distribution that has a mean of 0 and a standard deviation of sigma. So for every value, each value of x, y is normally distributed. Number 4 is what is called homoscedasticity, which says that the variance of y is the same for every value of x. The variance of y is the same for every value of x. Okay, I'll repeat the conditions once I finish. And number 6 is called unbiasedness, which states that the expected value or the mean of the errors are each 0. The expected value of the errors is 0. Your error is your EI that was at the back of the model. So the mean of these errors is 0. So number 1 condition is linearity. That is, x and y are related. Are linearly related. Number 2 is independence. That means each value of y does not depend on the other value of y. Number 3 for each value of x, y is normally distributed. And this is called normality. For each value of x, y is normally distributed with a mean of 0 and a standard deviation of sigma. Number 4 is homoscedasticity. Sorry, I always battle with this. Skedasticity, which says that the variance of y is the same for any value of x. And number 5 is unbiasedness, or unbiased, which says that the expected value of the error term is always 0. So these are the assumptions that must hold for simple linear regression to hold. Any question, please? Okay. Okay, last week we also looked at how you can check what is happening, linearity. We looked that you always check, because beta naught did not have any practical explanation, because beta naught theoretically was the value of y when x is 0. So for instance, if you're looking at a relationship between salary increase and work experience, number of years you've had in work experience, that means if you don't have any work experience, are you saying that this is the value of y, of amount of increase you get? Yes, theoretically, but in practical terms, it has no explanation. So because of that, we don't test beta naught. We always test beta 1 when you have a simple linear regression, or you test every other beta when we come to multiple regression except beta naught. So we looked at that also last week. When you're testing, there are two ways you can do it. You either look at your t-test value and read off the table, or you look at your p-value from the printout, and then you decide. So we have the testing beta 1 for simple, equals to 0 against H1, beta 1, is not equal to 0. So this one says no linear regression or no linear relationship. And H1 says there is linear relationship. So two ways you can do this. Either you check T value, or you check P value. If your T calculated is greater than your T from the table, you reject H0 and says there is a linear relationship. Or if you're using your P value, you go and look under significance. You see the word sig on the table, and you look at the value sig under the beta 1, and it says if P value is less than alpha percentage, that means you multiply this by 100 and you compare against whatever, you reject H0. For instance, in this example, our T value is 10.055. Our P value is 0.000, which is 0 0.000, which is equal to 0%, and is less than 5%. So we reject H naught. T-value here is 10.05. T from the table, let me see if there's anything. T from the table, we have n minus 2. In this case, our n is 11. That's n minus 2. I'm coming, I'm just, okay. I think I should use my table here. %, T-value, just a minute. Shucks. And table here. Okay. And table, T-table. That's 2.2622. 2.2622. So we reject H naught and decide that there's a linear relationship between X and Y. Now, other things you can look at the table for. The first one is called your R squared. R squared is explained as the percentage of the model or variation in model that is explained by the independent variable. So for instance, in our table here, our R squared is given as 0.669. You multiply it by 100, that gives you 66.9%. So what he's saying is that 66.9% of the variation in salary is explained by the number of years employed in the company. Multiply by 100, that gives us 66.9%. So you can say 66.9% variation in Y, that is salary, is explained by X, number of years employed. Okay, any question? Okay. Okay, let's go to today's work. Having said that about linear regression and built on what we did last week, we come to what is called multiple regression. The same thing that is happening in linear regression is happening in multiple regression. Only that this time you don't have, it's not one independent variable against one independent, but rather it is one dependent variable against more than one independent variable. So you have one y, but you must have at least two x's. So that's what is happening in multiple regression. In multiple regression, all the conditions we've said for linear regression must hold. Linearity, that means when you draw a graph, you should see a trend going in a straight line motion. There's a linear correlation or linear relationship between y and the x's. Number two, your y's are normally distributed. Number three, variance of y is the same irrespective of the x. Number four, your what's that for now? The y's don't depend on each other. Y at station 1 does not depend on value of y at station 2, does not depend on y at station 3, and so on. And number 5, the exterior value of your error is 0. So all those conditions will still hold in multiple regression. Only that you have more than two or more x's against one y. So let's look at our example here in week 9/10 of our lecture notes. You have salary and your model our model is still written the same way. You have your beta naught. You are going to have your betas depending on how many variables you have, how many independent variables you have. In this example, we had 1, 2, 3, 4 independent variables. So you're going to have y equals to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 plus error term. Now let's go to our table. Always read your coefficient from your unstandardized coefficients. Our y is given as salary. Our beta naught is constant under unstandardized coefficient. In this case, is minus 7.074. Our beta 1 is 0.368 plus 0.368. Our x in this case is age at last birthday, so we times age. Our next beta is 1.019, so you have a plus. Our X for that is years of prior experience, so I'm writing prior. Our next beta is plus 1.767. Our X in this case is years of employment, so I'm here writing years. Next beta is 4.520. And years of post-secondary education. So this is your regression line, your multiple regression or estimated multiple regression line. Remember, you cannot test your beta naught, but you can test each of the betas. So I can decide to test each of the betas. Suppose I'm testing beta 2. Let me see what was tested here. Oh, beta 2 has been tested. Okay. Okay, let's still go. We'll test beta 2. We're testing if there's linearity or if beta 2 contributes to the linearity of the Y of the model. So we're testing if beta 2 contributes to linearity of the model. So you have H naught, beta 2 equals to 0 against H1, beta 2 is not equal to 0. Two ways you can test, p-value or c-value. So our beta 2 is years of employment. Our X, the beta 2 is 1.7, sorry, beta 2 is 1.019 from the table. Corresponding to that, C is 1.744, and your p-value under significance is 0.088. We're testing at 5%. If you're not giving you test at 5%. So let's use P first. Multiply P by 100, that gives you 8.8%. And this is greater than 5%. Remember, we said if P is less than alpha, you reject H naught. If it's not, you accept H naught. So in this case, P is greater than 5%, we accept H naught. Or if you use your t value, you're going to look at t under 5%. Let's see. Our degree of freedom is n minus 2. Now, degree of freedom should be just hold on. Should be less. I'm trying to figure out the degree of freedom. Just hold on, please. In this example, we add total as 51. Residual is 47. I have to find out this, sorry. I have to try and calculate this. I'll find out later. So better still, let's go with our p-value. Now, p-value is 8.85%. We're accepting H0. H0 says that there is no linearity. So in essence, B2 does not contribute to the linearity of the model, although it's in the model, but it does not contribute. Next, we can also check if all the models contribute to the linearity. If beta 1, beta 2, beta 3, beta 4 contribute to the linearity. Now, if you're checking if all the model contributes to the linearity, you're going to look at the ANOVA printout of your regression. It's going to have ANOVA as the title, which this we're going to do in the lab soon. So if you look under ANOVA, that's what we're going to use, the table that has ANOVA. In this case, we have H0. Beta 1 equals to beta 2 equals to beta 3 equals to beta 4 equals to 0. H1, at least one beta I is not equal to 0. So in this case, you're going to have to use your F. So you're going to check what you have under F. For this example, our F gave us 109.055. You're going to look at a table called your F table. F is given as mean sum of square of regression divided by mean sum of square of residue or residual. So what we're going to do is at 5%, your F should be your mean sum of regression, the degree of freedom is 4, comma, for residual, your degree of freedom is 47. If you go to your F table, the numerator is along the row, so you read the numerator down. The denominator is on the left, you read the denominator along the row. Numerator along the column, denominator along the row. Okay. So in this case, our numerator is 4. Our denominator is 47. Now we don't have a 47 on this, so you can read between 40 and 60. Or you can put it on 60 or infinity. It won't make any big difference because your n is greater than 30. So let's go for 4 and infinity. That will give you 3.72. Or you could decide to read 4 and 40. That's 4.37. I'm taking 4 and 40. So it's between 4.37 and 4.14. When we're calculating our F from the table, you should pick out your table that I gave you and look for the one that has critical values of F as the title. What we're trying to do is to find out if all the betas contribute towards the linearity of the model or towards the model itself. So in this case, we cannot use T because all of them want to contribute. So you go and look for your printout that has ANOVA. In the ANOVA table, you're going to read off your F. F is given as mean sum of square of regression divided by mean sum of square of residual. So what that means is that the degree of freedom of the residual of the regression divided by the degree of freedom of the residual. In this case, our degree of freedom of regression was 4. That's our numerator. Our degree of freedom of residual is 47. So you take your F table. The numerator is along on top. You check 4. Your denominator is 47. The table I have in front of me does not have 47. It has 40 and 60. So I've read off 40, which is 4.37, and 60 is 4.14. So I guess my F for 447 must be between 4.37 and 4.14. Now, the rule is this. Just like you know, if F calculated is greater than F from the table, you reject H naught. So in this case, 109.055 is greater than 4 point whatever, either 4.37 or 4.14. So we're rejecting H naught. H naught says there's no linearity. If you reject H naught, you accept H1, which says there's linearity. So These betas contribute towards the linearity of the model. Otherwise, we can use, the other thing we can use is our p-value. In this case, you have 3.66 E-23. What this means is that 3.66 divided by 10 raised to power 23. Whatever value you get, you still get a 0%. 0% is less than 5%. That's of your p-value. That means you reject H0. This you read also from the ANOVA. So you either use the F or the significant ANOVA. Any question, please? Oh, you don't think you have the table? Okay. Okay, I'll see if I can download it and send it through to everyone because we'll be needing it in the next class. What does your table have? Okay, just a second. Let me check if my table is up here because I think I left my table somewhere here. Okay. 2.61. Oh, this is 10%. Let's see. We have, answer is 1%, 5%. So what is it giving us? Oh, sorry, I was reading off a, sorry. This is a 0.5%. Sorry about that. Okay, thanks. Okay. Sorry, this is 0.5%. I have to rub this off. Okay, the table should give you 2.61. And 50 should give you 2.56. Are we okay now? I'm really sorry. Sorry, I just assumed this book had a 5%. Sorry. Okay. Next, let's look at our R squared calculated. Your R squared calculated you get from the model. R squared in this case is given as 0.903. Multiplied by 100, that gives us 90.3%. So 90.3% of the variation in Y salary can be explained by the model. That's a high variation that can be explained. Okay. If you have to test more than one independent variable, this we have to do physically one-on-one when I see you. So I have to skip that and do that before we start ANOVA in the next class. Now let's see how we can predict using this model we have, and then we talk about how you can put in independent variables when you start. Okay. Our model is given as salary equals to minus 7.074 plus 0.368 age plus 1.019 prior experience plus 1.767 years of being employed plus 4.52 education. That's our model. Now we have an example where the age of the person is 35, no prior working experience, means this would be 0. He's worked for 12 years. And he has 4 years for secondary education. So his salary B minus 7.074 plus 0.368 times 35 plus 1.019 times 0 plus 1.767 times 12 plus 4.52 times 4, and that should give us 45.090. If you multiply by 1,000, that gives us 45090 as salary. So that's how you can predict. Okay. One more thing, you remember that we've talked about 5 conditions for multiple regression. Multiple regression decides to have a 6th one because the conditions for regression are the same for linear and multiple, but multiple regression is having a 6th condition. The 6th condition is called multicollinearity. Multicollinearity means that there is no correlation between the independent variables, or there's no interaction between the independent variables. That's the 6th condition we're having from. So how do I know if there's an interaction between the variables? You're going to run a Pearson correlation coefficient analysis between the variables and your Y. And when you run it, you're going to now look at it. So let's look at the table. We have correlations, the last sheet of our, sorry, I have to use magnifying glass. I can only see this. The last sheet, you have Pearson correlation. So you're going to look at that, if it's significant or not, and see. Luckily, it's already starred the ones that had correlation. So if there's a star there, that means there's a correlation between that variable and the other variable. So let's look at gender. Gender does not have any correlation with age, with years of prior experience, with years of employment, and so on. So if there is a correlation between any variable, X variable, then you have to extract those X variables and do away with them, because then your regression analysis is not going to give you the best. Or the other thing you can use to check multicollinearity is your tolerance level. So if you have high correlation, person's correlation is high, there's multicollinearity, that means you throw out the variables, or you go and check your coefficients. Your coefficient is going to give you what is called collinearity statistics. So it says that when your tolerance is very close to 0, then there is a strong relationship between that variable and other independent variables. So in this case, we have our tolerance for gender at 0.876. So it's not net 0. We have for age at last birthday at 0.039. We have years of prior experience at 0.153, so it's not net 0. We have years of employment at 0.084. And you have years of post-secondary education at 0.592. So in that case, there is no correlation between those variables because it's not very close to 0. Or if you're giving VIF, variance inflation factor, you look at them. The rule is that if they're greater than, I think, 50 or so, then you have to deal with them and let them go, and you don't use such variables. So in this case, we don't have any problem with this. Lastly, how do you determine what variables you can put in and what variables you can take out? There are 3 types of method. You have the backward elimination procedure, you have the forward elimination procedure, and you have the stepwise regression procedure. For me, I prefer the stepwise. Stepwise, what do you do in your stepwise? You go and look at your person correlation coefficient. And you look at it with your Y variable. And you look at the significance. So in this case, the last sheet, you have your annual salary is the last one. You can either take the annual salary, the last row, or you can take the last column, anyone. Your annual salary is your Y. Are you all with me? We're going to take our annual salary, which is our Y, and we're going to look at the significance. For gender, we're looking at 5%. For gender, our significance is 0.209. Multiplied by 100, you get 20.9%. 20.9% is greater than 5%, so we're not going to put gender in our model. Next, our significance total for annual salary for age at last birthday is 0.000. That means it's times 100, that gives us 0%. 0% is less than 5%, so we're going to pick that into our model. Next, we look at years of prior experience. That one is also 0%. We put that in our model. Next is years of employment at Beta. The significance is 0%, is less than 5%. You include that in the model. And lastly, years of post-secondary education. You have significance as 0%. You include that in the model. So you find out from here that the only thing we cannot include in our model is gender, because gender, the percentage is greater than 5%, so it's not going to contribute anything to our model, so you take it out. That's still the easiest. For the forward, you put everything in the model and you start looking at F value and taking the one with the smallest F value out, or P value. You go back again, you check the model again. So you have to run the model so many times, which I don't like. The same thing with the backward method and the forward method. You run the model so many times. So the best thing to do is the stepwise one, whereby you look at your percent correlation coefficients with your Y, see what it gives you, and then that determines whether you're going to include it or you're going to exclude it from your model. Any question? Is there any question? Anne-Marie, Ulemu, Abatina, Carrie, or Seri, Tulani. Who else is there? Luyando, Rowan. Any question? No, we're all cool. Okay. Thanks for coming. Next week, Monday, I'm on leave. Because of the long weekend, I'm taking leave next week, Monday. Sure. Next week, Monday, I'm on leave, so because of the long weekend, so I won't be around. Our com lab for multiple regression will be the upper Monday. So our com lab will be upper Monday when we come back from the long weekend, and you can let me know if you want me to go through this again in class before we do the ANOVA, because then we have to do our ANOVA and then do the com lab for regression and ANOVA. So please, if you're having any problem this week, next week, let me know before we have the class on upper Monday after the long weekend, so that I'll know what I'm going to teach in class. And now I'm going to set my class. Okay, thanks so much for coming. Have a nice evening. Stay blessed. Bye.